Hi there, Physics 131. So this is the pre-class reading video, just to give you a quick overview of the reading for class 16. But before we do that, this is a new week. I guess we're on week 6 of the class. So let's just look actually at the course website for a minute. Okay, so there's term test the next term test is November 21st. So when you go to these practicals, we're now on practicals 4. And the basic idea with the practicals is that they deal with the material from the week before. So this is all chapter 5 stuff. This week, we're starting in on chapter 6 in the lectures, but then the idea is that you kind of solidify that information when you actually work with this stuff hands-on in the practicals the following week, if that makes sense. And then, in fact, the problem set, which is all on chapter 5, circular motion stuff, is due on October 22nd. And again, this is 20 multiple choice questions that you have to go on to Quarkus and submit. So I highly encourage you to print this one out, use pen and paper, and write out your solutions to all these 20 questions. And then when you've got it, go on to Quarkus and type in the answers. And there's a mix of conceptual questions as well as numerical questions, and there's 20 of them. And then plus I have posted, I think it's about 17 just practice problems at the end. These are not at all for marks. The problems from 21 to 37 are for students that may wish to do some extra practice work. They're fully and completely optional and not worth any marks. So that's kind of an overview of just where we're at in terms of weeks. So now we're on to chapter 6, which is called Impulse and Linear Momentum. And there's a rocket going out into space. And ships, propellers push water. In turn, the water pushes the ship, accelerating it. A rocket pushes its fuel exhaust, and that in turn accelerates it, even though there seems to be nothing to push against. So section 6.1 is called Mass Accounting. And the idea here is we're talking about conservation laws. And there's going to be, this is about linear momentum, so there's going to be conservation of momentum. And I think they try to analogize this by asking you to think about conservation of mass. So you've probably observed countless physical processes in which mass seems to change. For example, a mass of log in the campfire decreases as the log burns. What happens to the lost mass? Well, we think that if you add up the mass of all the smoke and everything, all the ash, you would get that same mass again. So there's a lot of experiments to prove this idea that matter doesn't just go away, it just gets turned into different forms of matter. So that's the idea here. Initial mass of the system plus any new mass entering the system, or minus the mass that's leaving the system, gives you the final mass. It's sort of like the initial plus the delta equals the final. That's the conservation of mass idea. And you can even put it into these bar charts. There's the initial mass plus the change in mass, and it could be positive or negative, equals that final mass. So mass is an example of a conserved quantity. A conserved quantity is constant in an isolated system. Constant means not changing over time. So when the system is not isolated, the quantity may change. However, if it does, we can always find another system in which the quantity is constant, just make a bigger system. And section 6.2 is called linear momentum. We know that mass is an example of a conserved quantity. Is there a quantity related to motion that is conserved? Well, sort of depends again on how you define your system. But what we do is in this chapter, we introduce something called mass times velocity to give momentum. And you can do a few experiments in collisions that gives you this idea that somehow you can find an isolated system in which the quantity, mass times velocity, remains constant. So we define linear momentum as the letter P. It's a vector, so it has a little arrow over top of it. And P is equal to m times v, where v is the velocity vector and m is the mass of the object. So an object that's moving has a momentum. Okay, so since it's a vector, you have to have its components, x and y components. And there is this conservation of momentum, meaning that if you have a totally isolated system and there's no net external forces on the system, then the momentum before, it might have different parts to the system, equals the momentum final. It doesn't necessarily change. And so they give examples of two rollerbladers pushing away from each other. And so the normal force and the gravity force cancel out. You get zero net force on the whole system, I guess. And so that's why momentum is conserved in that case. And that's all the reading for Monday. And I'll see you on Wednesday's video. Bye for now.